Hello, everyone. Um, First, I'd like to thank the organizers. It's my great pleasure to speak on geometry and the tacos. To get started, let me share my screen. Okay, so I hope everyone can see it. Okay, so the talk I'm going to present today is about SU3 structures and the Type IIA flow. So as we know, the theme of this tacos session is geometry and physics of non-Kähler Calabi-Yau manifolds. And a great motivation for Calabi-Yau manifolds actually comes from string theory. So here's my plan of talk today. So first, I will give a brief introduction to the backgrounds of my talk. As you can see from my title, there will be two parts of my talk. So the first part, okay. So this is like the first part. It's about SU3 structures, and in particular, what's the relation between how SU3 structure rises from superstring theory. And I don't claim any originality from this part because this is already well known in the physics community since 1980s. What I'm trying to do is give a more mathematically oriented introduction to this thing to help my colleagues understand what is going on. Of course, this is really based on my very limited understanding of this situation. So it might not be the best material for you to learn about this. And then I'll talk about some of my own joint work with Feng, Picard, and Xiangwen Zhang. So that's the second part. So this is concerned on geometric flows to study the Type IIA string equations. Okay, so I will first talk about what is the Type IIA flow we introduced and the main results, and then I'll say something about applications of our flow and also give some examples. And finally, if we have time, I'll also mention the proof of our theorems. Okay. So the main references for my talk are the following. So the first one is by Strominger. This is an expository article on how we get this Calabi-Yau structure from complication of superstrings. Okay, it's very beautifully written. I highly recommend it. And then the second and third references are our very recent work where we introduced the Type IIA flows. So these appears on arXiv at the end of last year. All right, so let me begin with the backgrounds. Okay, so we're talking about superstring theories. So first, string theories are some 10-dimensional theories. So in particular, there is a 10-dimensional manifold, which is Lorentzian, and it's called M. And over M, there are various fields, which I'll explain in detail later. So you can just think of these fields as sections of certain vector bundles over M. And we know there are actually 5 kinds of string theories. There's type 1 string and type 2A and type 2B, and there are 2 kinds of heterotic strings with different gauge group. And in general, the string theories are very complicated to describe, and they are not easy to study either. Okay. So we want to somehow simplify the things we study. And there are actually a few ways to make life easier. So first thing one can do is to impose what's called a supersymmetry. So this is a kind of symmetry which exchange bosons and fermions. Another thing is that, okay, string theory is 10-dimensional, but our physical world, usually we believe it's 4-dimensional, like space-time, okay? So there's this idea of dimensional reduction, or you can call it complexification, that is to assume that the 10-dimensional manifold, this Lorentzian manifold, is actually a product of the Minkowski space-time with some 6-dimensional manifold called X. So this X is called internal manifold, and it's a Riemannian. It's come with a Riemannian metric because the Lorentzian part is taken care of by the Minkowski spacetime, and usually we assume X is compact and very small in scale. So we do not observe it by our naked eyes. And there's a third assumption. It's called flux-free or torsion-free, which I'll explain later. Basically, this is by assuming certain field to be 0. Okay, so if we assume all these 3 simplifications, we impose all these 3 conditions, and Candelas, Horowitz, Strominger, and Wheaton in '85 show that this X, this internal manifold, actually is something very special. It's a Kähler manifold with Ricci flat metric. So later they call them Calabi-Yau manifolds. And this Ricci flat condition and Kähler condition actually gives rise to a complex Moore-Ampere equation, which was solved by Yau. So this is like the Yau's solution to the Calabi conjecture. So we get lots of examples of such things. So in particular, what we have is X is a 6-manifold. There's a Riemannian metric G. And besides that, we have a almost complex structure J compatible with G. And J and G together, they'll give a Kähler form omega, and also there's a holomorphic volume form known as capital omega. Okay, and in this flux-free case, the J is integrable, so we have a complex manifold, and omega is closed, so this is a Kähler manifold, and finally this omega is parallel under the Levi-Civita connection. So this is the Ricci flat condition. Okay, so what we get is an integrable SU3 structure on X. Okay, so this is the first example, I guess, also the simplest example of SU3 structure arising from complexification of superstrings. However, if we want to a more realistic theory of strings, especially in considering the particle physics, a realistic theory of particle physics, we need to consider flux compactifications. So we cannot assume the flux is 0. Okay, so we just keep the other two assumptions, supersymmetry and the compactification, this dimensional reduction thing, but we allow the flux to be non-zero. Then we got this flux compactifications. And this leads to a more complicated system of equations on X. For example, if we're considering heterotic strings, then we get what's called the House-Strominger system. If we consider the type IIA or type IIB strings, and I guess the first mathematical formulation of them is by Tomasiello and Zheng and Liang. So to summarize, because we have less constraints, so we get more general kind of geometry. So in particular, get non-integrable. We may get non-integrable SU3 structures on X. So this leads to some non-Kähler Calabi-Yau threefolds. Actually, I think non-integrable is not a very good way to put it. Maybe it should really call it a partially integrable, because in many cases there's still some kind of integrability there. For example, in the heterotic or type IIB case, we are working in the realm of complex geometry in that case. So the almost complex structure is integrable. And in the case of type IIA strings, this is about symplectic geometry. So the symplectic form. we always have a closed symplectic form. Okay, and also you know that there's a mirror symmetry between type IIA and type IIBs, which relates the symplectic geometry and the complex geometry. Okay, so this is the rough idea of how SU3 structures shows up in superstring theory. In particular, if you have flux, you allow flux compactifications, you'll get some non-integrable SU3 structures. So now I want to give more detail about this procedure. So let me take the heterotic superstrings as an example. So as I mentioned before, in the superstring theory, the ingredients, there are many ingredients. The first one is a 10-dimensional manifold. Let's call it M, okay? And there are various fields. You think of them as sections of certain vector bundles over M. So they're both bosons and fermions. So for the bosons, there includes, in the heterotic string, there's a Lorentzian manifold G on M. There's a function, scalar function phi. It's called a dilaton function. And also there's actually there's some extra vector bundle. It's a gauge bundle. So it's a G bundle with structure group G. And there's a connection, a G connection on this vector bundle. It's called curly A. And also there's this local potential B. And there are some fermions. They are called the gravitino, dilatino, and the gaugino. So these are just the super partners of the bosons. So gravitino phi or psi corresponds to this Lorentzian metric G. Dilatino corresponds to the dilaton function, and gaugino corresponds to this connection. Okay, so roughly you can think of these fermions are somehow sections of spinor bundles, or spinor bundles, tensor of spinor bundles with some other bundles you can construct from either from the tangent bundle or from the principal G bundle. And all these bosons are just coming from the tangent bundle or the gauge bundle. Okay, so these are the fields. And in the string theory, there's a Lagrangian or action. So I guess the mathematical terminology for this is a functional. Let's call it S. So this is basically this is a function of all these fields. So it looks like this. So here I'm only giving what's called the bosonic part, because of all these expressions involves only bosons. So I'm ignoring the fermion, any fermions, because later we're going to put all the fermions to be 0. And also there's a ... here, which actually also includes higher order corrections terms, which in the order of alpha prime. So this alpha prime is a coupling constant. Okay, so this RG is the scalar curvature of the metric. So this is like some part looks like the Einstein-Hilbert functional. If you only have the Einstein-Hilbert functional, then that's the supergravity. But there's also the matter part. So, and also there's this thing H. So H is called the axion 3 form, or the flux. So locally, H can be written as D of this potential B and alpha prime times this Chern-Simons terms involving the Leverage-Vita connection of the tangent bundle and also this connection A on the gauge bundle. Okay, so anyway, so the goal of the superstring theory is to solve the equation of motion, that is the Euler-Lagrange equation of this functional S. Okay, and we know that the general principle tells us this Euler-Lagrange equation would be, or in other words, the equation of motion would be a second order equation in terms of all these fields. Okay. So now let's talk about supersymmetry. So this action, as we see, is really complicated, and we really need some impose some symmetry to simplify it. And the physical consideration tells us we should consider supersymmetry. And if we have a string theory with supersymmetry, what we get is what's called superstrings. Okay, so the assumption of supersymmetry is that this function or this action S up to first order of alpha prime is invariant under the supersymmetric transformation. But in practice, we don't really observe supersymmetry. So the supersymmetry actually breaks when higher corrections are incorporated. And in this case, we can write down the infinitesimal supersymmetric transformations. So these are chi, psi, lambda. These are the fermions. And this supersymmetric transformation is actually generated by some, the generator epsilon is the spinner. Okay, it's what's called a marijuana wild spinner. Okay, and the right-hand side, I'm writing down some of them. Okay, so this F is the curvature of the gauge bundle. These gammas are the gamma matrices, which acts on spinors. Okay, and H is this flux reform we mentioned before, and nabla is the Levi-Civita connection or spinor connection on the manifold. Okay, there are some terms of which are involves the quadratic terms of fermions. So these are the variation of the fermions. And the variation of bosons consists of all terms involving fermions. Okay, so these are the supersymmetric transformations. Okay, so now let's talk about complication. So here the assumption is that our 10-dimensional manifold M is a product of the Minkowski spacetime with a Riemannian 6-manifold X, and which is compact. In this case, actually, there's the only possibility is this n equals 1 supersymmetry, and this implies all the fermions must be 0 under the assumption of compactification. Okay, so if we go back to the last page, we see all the fermions should be 0, so all the left-hand side of this is 0, and also these terms drop out because they involve quadratic terms of fermions. And the bosons, they are naturally supersymmetric, because the right-hand side here are 0. So we only have these 3 equations to solve. These are 3 equations implied by supersymmetry, and also other. Okay. So in particular, the second equation here is called the Killing spinor equation. So because this really says, okay, epsilon, this spinor is actually parallel under some connection, which this is the spin connection twisted by the flux term. Okay, so you can say this is just saying the spinor epsilon is parallel under some twisted connection, or this is a connection with torsion. Okay, so the point is that all these equations, they are actually first order equations, or even lower order, like this one is even lower order. And in many cases, we observe that the supersymmetric equations, they automatically imply the equation of motion, which is second order. But this is, I don't think there's a proof for this in the most general case. But the simplest example of this is like, let's put H equals 0. Okay, so then this is just saying, okay, we have a parallel spinor. Okay, and this implies Ricci flatness. The metric is Ricci flat, which is the Euler-Lagrange equation of the Hilbert-Einstein function. Okay, that's the simplest example. This is actually the example of supergravity. Okay, so by this compactification assumption, so this M is actually the product of R4, R13 with X. So actually there's a corresponding decomposition of the spinor bundle. So this spinor bundle S plus can be decomposed as a tensor of the plus spinor bundle of R4 and X, direct sum with the tensor product of the spinor bundle of the minus spinor bundle of R4 and X. So using this decomposition, all these equations here, they are actually spinors on M. It actually reduced to first order spinor equations on X, because on the R4 part, it must be something parallel. This is one can show. And in particular, this Killing spinor equation here will become something like this. It's just like there's some parallel spinor. There's spinor on X, which is parallel under some twisted connection. Okay, and in fact, this single equation implies there's a natural SU3 structure on X. And there are actually two ways to see it. The first one is more geometric. This is like a holonomy argument. So on X is 6 manifold. So there's this spin 6 group acting on the spinors, but this group is isomorphic to SU4. So it acts on the spinor bundle, and at each point, it's just C4. So this action is just the usual standard action, SU4 on C4. And if we look at a point which is not 0, that is corresponds to the spinor eta, then its stabilizer is SU3. Okay. And you look at the image of this SU3 in the SO6. So because we know the spin 6 to SO6 is a double cover, and SU3 sits inside spin 6. So you look at the image under this 2-to-1 covering map, and in fact, the image is just gives a standard embedding of SU3 in SO6. Okay, so basically this means if we have such a spinor, we reduce our structure group of our Riemannian manifold, which is SO6, to SU3. So we get an SU3 structure. And there's a more explicit way to construct this SU3 structure. So because you have this spinor eta, which is parallel under some twisted connection, then you can cook up this almost complex structure J by this formula. So this because this C4, this spinor bundle has a complex natural complex structure there. So you can define what is the dagger, that's like the conjugate transpose, and also what's its transpose. These are just the elements in the dual of this the spinor bundle. Okay, so you can use this formula to define some tensors, and this J turns out to be an almost complex structure, and this capital omega turns out to be a holomorphic volume form or complex volume form. So you do get this SU3 structure. Okay, so this is how we get SU structure or Calabi-Yau structure from supersymmetry and consideration of compactification. Okay, so now let's turn to some more concrete case. That's the case of type IIA strings. So we know the first thing I want to emphasize is that SU3 structure is actually rather special compared to general SUN structure. So if you have a SUN structure, then you have the following things. You have an almost Hermitian manifold. So you have a Riemannian manifold X with metric G, and there's an almost complex structure J compatible with G, and then there's a corresponding Kähler form omega. And also you have this complex volume form, capital omega, which we write as phi plus I phi hat. So phi and phi hat are just the real part and imaginary part of this complex volume form. So this one, you can think of this as a smooth section of the canonical bundle. So for SUN structures, if you have J, if you have omega, and then you can find what G is. So J and omega define G. And also J is determined by capital omega. So in other words, to characterize this SUN structure, you only need capital omega and little omega. Okay, but there's something more algebraic miracles in dimension 6. So only in dimension 6, you have the following further reduction. You find that this imaginary part of your complex volume form is actually determined by the real part. So you only need the real part to get the capital omega. This is what's called the Hitchens construction. So we only need little omega and the real part to characterize an SU3 structure. Okay, and in this way, we can write down the type IIA string equations. Again, after consideration of superstring, supersymmetry, and the simplification. So the equations are the following. So first, this omega is closed. So you have a symplectic form, symplectic geometry. Also, the real part is also closed. And naturally, this is SU structure. So the real part is primitive. So omega wedge phi is 0. And finally, you have this, the other equation, d lambda d of this expression is rho a. So this norm of phi square is a scalar function defined in this way. Because you have phi, you can define phi hat. And their wedge product is a top form, which is a multiple of the volume form. So that's multiple is called the phi norm square. And this lambda here is the contraction by omega. So this is like a dual to wedging with omega. So this is, I guess, standard for the audience today. And finally, we have this rho A. This is really some current. It's actually like it's a Poincare dual to some linear combination of special Lagrangians calibrated by the real part of the complex form, calibrated by phi. But we can ignore that today for today's talk, because later we're going to put this to be 0. So this is actually one of our contributions to clarify the meaning of this iteration. So basically, we only need to solve for this pair omega and phi, and this phi hat is related to phi by the Hitchens construction. But there's another algebraic miracle in dimension 6. So that is not any, in general, not any 3-form phi comes from in the case of SUN structure, not any real form comes from the real part of the complex volume form. But in dimensions 6, there's something very special, that is this phi is stable, which means there's actually the set that's of the real 3 form that comes from a real part of a complex 3 form, a complex volume form, is actually an open set. So suppose you already have such a phi coming from an SU3 structure, then if you deform this phi a little bit, then it still comes from another different SU3 structure. So this SU structure somehow is stable under perturbation. Okay, it's because of this stability we can use geometric flow to deform SU structure, or to improve our SU3 structure. Because if you have originally you have a phi from an SU structure and you deform it, you know it still comes from another SU3 structure. And that is very, so it's just because of the stability we decide, okay, why don't we try to use geometric flow to study this type IIA strings? Because if there's some miracle, we should embrace it. It doesn't happen in any other dimension. Okay, so now let me introduce the type IIA. So this is really a parabolic approach to the type IIA equations, sorry, which is here. And the idea is very simple. So we fix a compact symplectic 6 manifold X omega, and we want to solve the PDE. dt of phi is d lambda d of this term minus rho a. So basically, you want the right-hand side to be 0 at time infinity, which solves this third equation in the type IIA strings. And we want some initial data satisfying the initial 3 form is primitive and also closed. And we hope that this primitiveness and the closeness of phi can be preserved along the flow, which means the first two equations here can be solved automatically. And then if the flow converges, then it will converge to a solution to the type IIA equation. And obviously the stationary points should be solutions to them. Then in that case, we know the stationary points must be solutions to the type IIA equation. Okay, so this is our hope. So there are many features of this flow. So first, this is a flow of 3 form. So another famous example of flow of 3 form is this G2 flow, and such as Bryan's G2 Laplacian flow. And in fact, there is a connection between our flow with the Bryan's G2 Laplacian flow. Okay, the second thing is that heat transient construction actually tells us the flow of the 3 form phi actually induces a flow of J, because this phi determines the full complex volume form capital omega, and the capital omega determines J. So from phi, you get capital omega, and then you get J. So this induces actually a flow of almost complex with J that should be always compatible with our Sink-Blackman form. Therefore, our flow can be used to find optimal almost complex structures on a fixed symplectic manifold. In literature, there's some other flow like this. For example, there's a Le-Wan's anti-complexified Ricci flow. And in fact, there's also a connection between our flow with Le-Wan's anti-complexified Ricci flow. And finally, so there's formally you can check there's the closeness and primitiveness of the 3 form is preserved under this flow because this term here is the evolving term is always primitive and closed. Okay, so it inspires us to introduce what we call the type IIA structure. That is a triple M omega phi, where we have a symplectic 6 manifold M omega, and this phi is a closed primitive positive 3 form. This positivity simply means from this 3 form phi, you get this J, and this J is compatible with omega. So you get a Riemannian metric. Okay, and formally, our flow preserves type IIA structure. Okay, so now let me state our main theorems. So from now on, we'll just study the source-free case. That is, we don't have this annoying source term rho A. So our flow is just like this. We evolve the phi, dt of phi, by this term. And with initial data that phi naught is both primitive and closed. So this is the flow we're studying. Okay, so our first theorem says this flow has short time existence and uniqueness, and also it preserves type IIA geometry. So this is very simple to state. However, I think for any geometric flow, this is like the most fundamental result one needs to prove. Okay, our second result says this flow actually we introduce preserves integrability of almost complex structure. That is, if your initial data phi naught whose associated J is actually integrable. If J naught is integrable, then actually the evolving almost complex structure J stays integrable, and the flow in this case actually will converge to an integrable SU3 structure. So in this case, this J is still evolving, it's still changing, but it's always integrable. And then finally, it becomes the optimal J, giving us an integral SU3 structure. So you can think of this as like a symplectic version of, this actually gives us a symplectic proof of the Calabi-Yau theorem, but only in dimension 6. So if you compare this with Kähler-Ricci flow, for Kähler-Ricci flow, the case is to fix the complex structure J, and you are improving the Kähler form omega. And here, our case, we fix the Kähler form omega, but we are improving our complex structure. Okay. To state our third main result, I need to introduce some notation. So let G be the associate metric, Riemannian metric, that is from our data phi, from our omega phi and omega, we can get J and omega, and this gives us this metric G. So there's it's Riemannian metric. And Rm is the curvature tensor. So this is with the Levi-Civita connection of G. And also we define this function U to be log of norm phi squared. So in this case, norm phi squared is always positive. So this is a globally defined smooth function. Okay, so our third theorem gives us a criterion that's when our flow can be continued. So suppose we have a solution to our flow on a finite time interval 0t. And suppose we know that there's some constant c such that over our manifold x and on this time interval, the function u plus, which is log phi squared, plus the norm of the Riemannian curvature is bounded. Then we know this flow can be continued by a short amount of time, epsilon. Okay. So this flow can be continued. And moreover, we have this estimate that u is always bounded from below by the initial date. So that's why we only need the upper bound of u here. We don't need to put the absolute value because the lower bound is automatic. So basically, the theorem tells if our flow has a finite time singularity, then either u blows up or the curvature blows up. There are no other possibilities. And finally, there's some monotone quantities. And we know in Hitchin's work, when he introduced his construction, it comes naturally with a functional called Hitchin's functional. And this Hitchin's functional in this case can be written as the integral of e to the u, so integral of norm phi squared. And this quantity actually is monotonally non-decreasing along our flow. But our flow is not the gradient flow of the Hitchin's function. Okay, so after stating our main results, I'd like to apply our flow to some special cases. And also, these are very nice examples. And the setup is the following. So this is like, I guess this is aligns with the second session of the tacos series. This neo-manifold and solved manifold techniques. So we're going to run, basically, we're going to run some of our type IIA flow on some, on this homogeneous symplectic half-flat manifolds, and to use our flow to find optimal almost complex structures. This is what we're going to do. And these homogeneous symplectic half-flat manifolds are either neo-manifolds or solved manifolds, at least in the examples we are considering. Okay, so first let's recall that the symplectic half-flat structure it's just a type IIA structure. So we have a symplectic form, a symplectic manifold X omega And also we have this phi, it's a real part of the complex Spalding form, which is closed, with the extra condition that phi square, the norm phi square, is a constant. So this is what's called a symplectic half-flat structure. Many examples of symplectic half-flat manifolds are homogeneous of the form G quotient by gamma, where G is a six-dimensional Lie group and gamma is a co-compact lattice, meaning gamma is a discrete subgroup of G such that G over gamma is compact. And also in this case, we want the symplectic form and phi to be G invariant, closed differential forms. So they descend to this quotient. And it's very easy to see that these homogeneous symplectic half-flat structures are preserved under the type IIA flow because the symmetry is preserved. Okay, so if we, in this homogeneous setup, then we have more monotonicity formulas. This is because we know all the scalar functions in this case are actually, they're constant by the homogeneity. So many terms drop out if you compute the evolution equation of such quantities along our flow. So we get more monotonicity formula. The first one is that e to the minus u is actually non-increasing, and its time derivative is characterized by the negative of the norm of a Eigenhus tensor. And we know when this is 0, we get an integrable complex structure. And if we involve the norm square of an Eigenhus tensor, we get also something, the time derivative is also something non-positive. So the Eigenhus tensor norm square is also non-increasing along our flow. In other words, the evolving complex, almost complex structure is becoming more and more integrable in some sense. So with this 2 and this Ricci minus j is really the j anti-invariant part of the Ricci curvature tensor. Okay, so with this 2 monotonicity formula, we can easily prove the following corollary. So suppose we have a homogeneous symplectic half-flat manifold. This is like the initial data is homogeneous symplectic half-flat. And then the type IIA, and we run the type IIA flow with this initial data. And suppose we know this flow exists for all time, that is, we have long time existence, then there exists a family of compatible almost complex structures, J, such that the Eigenhus tensor can be arbitrarily small. Okay. So this is actually very easy to prove because you can rewrite, if you combine these 2 equations, you can find that you look at the second derivative of e to the minus u, okay, then this is going to be non-negative. So e to the minus u so this is like a convex function. But the first derivative is non-positive, so this is monotonely decreasing. So you can plot this function e to the minus u and t. It's decreasing and it's convex. And also we know it has a lower bound, 0, because the e to the minus u is always positive, so it has a lower bound. And what you know is that if this flow exists for all time, then this function will the t goes to infinity, then it has some lower bound there. So at the time infinite, when time goes larger and larger, then the tangent of your curve must be getting closer and closer to be horizontal. So that's to say that the time derivative. This is like the slope of the tangent. It's just the derivative here is approaching 0. So that's why we get this result here. So this is very straightforward. So you can think of this result as that the behavior of our flow on this homogeneous setup actually tells us whether we can have how good an almost complex structure we can have. In this case, they can be getting very close to be integral, but in many cases, the manifold itself is non-Kähler, so it does not admit any Kähler structure. So this n will not converge. In other words, you can get arbitrary, almost compatible, almost complex structure with arbitrary small eigenhuge tensor, but that cannot be 0. Okay, so let me just present some examples. So the first example is a neo-manifold constructed first by De Bartolome and Tomasini. So in this case, the flow exists for all times. So our previous corollary applies, but this manifold is a neo-manifold, it's non-Kähler, so we can get arbitrary, compatible almost complex structure with arbitrary small eigenhuge tensor, but it's also homogeneous, but it can never be integrable. I think a more interesting example comes from a soft manifold constructed by Tomasini and Vessoni. So in this case, the flow blows up in finite time because this function u blows up. So recall from our estimate. However, when the time tends to this limiting time, the underlying almost complex structure actually converges. So this limit exists. And this converging or limiting almost complex structure in some sense is an optimal one. It is a harmonic almost complex structure, which I'll explain later. It's a minimizer of the eigenhuge tensor among all compatible homogeneous almost complex structures. So recall, this is a definition of Low and Wang. That is, if you have a symplectic manifold, the compatible almost complex structure is called harmonic if the associated Ricci curvature. So this is a Riemannian Ricci curvature tensor. It's actually J invariant. That is, we have this kind of symmetry. And we know this kind of symmetry is always satisfied by Kähler manifolds. But there are examples of a non-Kähler Hermitian or almost Hermitian manifolds still having this symmetry. So when this manifold is almost Kähler, this J is called a harmonic almost complex structure. And in this case, we do get one. And in fact, we find this harmonic almost complex structure by using our flow. They are the limiting almost complex structures. Okay, we also have some other examples, but let me just not talk about them. And we have, I think, 10 more minutes. So let me say a few words about our theorem. Probably I'm only going to say about the proof of theorem A. In fact, this turns out to be I think the most interesting proof in our work. So the theorem A is, just tells us this type IIA flow we introduced has short time existence and uniqueness. The second part, it preserves type IIA geometry is relatively easy to do. Okay, so this is our flow, and the initial data satisfies closeness and primitives, and also positive, which means we have a compatible Riemannian metric. Okay. So the first thing is, if we'd like to have a parabolic equation. If the flow is parabolic, then this is the short time existence and uniqueness is automatic. then we're in good shape. But the thing is that this flow is only weakly parabolic, just like Ricci flow. But in some sense, it's even weaker. The parabolicity is even weaker compared to the Ricci flow. It's actually more degenerate than the Ricci flow, as we'll see later. Anyway, so usually there are two methods to deal with weakly parabolic equations. Like there's a Hamilton's-Nash mode, there's implicit function theorem, and also there's a Dieterk streak. In the case of Ricci flow, both methods work, and you only need one of them. Okay, either you use Hamilton's theorem, that works, or you can just simply apply Dieterk streak, reparameterize the flow, and you get a strictly parabolic flow, which is equivalent to the Ricci flow. Okay. So in our case, the first natural thing to do is we should just try this methods there. Okay. If we want to apply the Hamilton theorem, then we need an integrability operator. It's a first order operator that kills, or some more or less kills, the right hand side. And indeed, there's a natural one to do because the right hand side here is the exact zero. If we apply d to it, it's 0. So this is a natural integrability operator. And if we use this to apply Hamilton's theorem, then it kills some part of the kernel of the symbol of the right-hand side, principal symbol of the right-hand side, but not all of them. We still get a degenerate equation. Then that's not, which means this, if we just apply Hamilton's theorem, it's not good enough. This flow is more degenerate compared to the Ricci flow. Okay, so next we may want to try the Dieterk streak, that is to reparameterize our flow. However, when you try to reparameterize your flow, immediately you realize that you should reparameterize everything, because you use the vector field you use in the Dieterk streak actually is evolving. Okay, it's you need to solve it. You don't know it beforehand. So if you do this Dieterk streak using a vector field like what Dieterk did in the case of Ricci flow, this will actually make the symplectic form unknown. Originally, omega is fixed, but after reparameterization, omega is evolving by an unknown vector field, so it's becoming unknown. In this case, one needs to consider a coupled flow for the pair, the 3-form and omega, if you want to implement the Dieterk streak. Okay, so this actually inspire us to consider the following coupled flow, where you evolve phi by, this is what we already have, then you add some Lie derivative term, but this part of Lie derivative, it's a d of, and there's something extra I will explain later. And also you do evolving omega by this something, the first part, or the leading order term of the Lie derivative, because we know there's a this Cartan's formula. Okay, so this is like the leading term. It's like this is like second order term. This one is usually first order. Also, we have this condition on the initial data, so all of them to be closed, and it's primitive initially. And this vector field V is a properly chosen Dieterk type vector field. It depends on phi and omega. So if you only have these two terms, then this is really like the Dieterk streak, because we are expecting this phi and omega to be closed along the flow. So this extra term drops out. So we only need to keep this exact terms here. But anyway, we really need this rat term, the extra rat term. This is an extra regularization term. of the reparameterized flow by V. And this term actually we expect to be 0 because if we have a SU3 structure, then we know this omega is phi plus I phi hat. This is of type 3, 0. And omega, this is type 1, 1. So, which means both phi and phi hat should be primitive, and this one should be 0. So we expect this term to be 0. But however, we do not know a priori because we are considering a coupled flow. So a priori, we should think of phi and omega are they are independent variables. So we don't know whether they are primitive, it's primitive or not. So we add this term simply to improve the parabolicity. Because if we don't have this red term, then later we're going, if we just compute the symbol, we can show that it's still degenerate even after applying Hamilton's theorem, because in this case, we still have an integrability operator D on the right-hand side. Because everything on the right-hand side are D exact. So we still have integrability operator. And if we don't add this red term, then if you compute the symbol, there's still some degeneracy in the non-primitive direction. And a priori, we cannot assume phi is always primitive with respect to omega. They're independent because we are treating them as independent variables. So this red term actually fixes this degenerate directions. Okay, so this flow, this double star flow we're considering, again, has the integrability operator D, and by Hamilton's Nash-Mills theorem, it has short time existence and uniqueness. So we also see that this preserves closeness of phi and omega. So we can add this this Lie derivative, the missing part of the Lie derivative back. So these two terms are the Lie derivative. So this one is the Lie derivative omega. Okay, and then we can reparameterize. So what we show this, we get short time existence and uniqueness of this flow here with this extra red term. And next step is we apply maximum principle to this flow by showing that the primitiveness of phi is preserved. So the red term vanishes. And in this flow, this omega is a constant. Doesn't change after reparameterization. This is just by a maximal principle argument. And so we get, for any solution to this flow with such initial data, we actually get the solution to the original type IIA flow we are considering. This is the type IIA flow we are considering. Okay, so let me summarize a little bit. So we proved the short time existence of the type IIA flow by a combination of Hamilton's Nash-Mills theorem with the Turk streak, plus an extra regularization procedure. So you can see this is really far more complicated than the Ricci flow case. So the uniqueness can also be obtained in this way as well. But alternatively, later we need to study the induced flow of the metric G and U to get the estimates. So we can also do that, prove the uniqueness by applying Hamilton's Nash-Mills theorem to the induced flow of G and U. But this alternative approach calls for a careful study of the type IIA geometry. Since I think the time is up, so I'll skip this type IIA geometry part. So basically, we proved there are lots of nice geometric consequences of this type IIA structure. So in particular, we show this almost complex structure J showing up in a type IIA Geometry is very special compared to a generic compatible almost complex structure. It has lots of nice properties, like there's a holonomic interpretation, and also there's some extra symmetry of eigenhuge tensor. There's a linear symmetry, and there's a quadratic identities, and also there are curvature identities. And all this helps us to really simplify or derive the evolution equation of the metric of the function u and so on. And this also leads us to establish our estimates. Okay, so let me just stop here and thank you for your attention.